Welcome friends. In this session we are going to discuss noise performance in AM receiver using envelope detection. Here AM used is double sideband full carrier or standard AM. The noisy model of AM receiver is shown in figure. It consists of input AM signal, that is a type of double sideband full carrier amplitude modulated wave and denoted by S function T. During transmission, because of a noisy channel, this standard AM signal is affected by channel noise, which is additive in nature and denoted by W function T. This channel noise is also called front-end receiver noise. Now this noisy received signal is first passed through bandpass filter and we get signal X function T. This bandpass filter converts W function T into a narrowband noise or filtered noise, which is compatible with the input standard AM signal. After this, X function T signal is passed through envelope detector, that is the detection process of double sideband full carrier AM wave, and we get output Y function T. Here, output of envelope detector may contain some DC component. Hence, there is a requirement of blocking capacitor as shown in figure, and results output Y0 in the scaled version of message signal and noise. As we know that standard AM or double sideband full carrier is given by equation S function T equals to AC within bracket 1 plus Ka M function T into cos 2 pi FCT. Here Ka is called amplitude sensitivity of the modulator, which is equals to 1 upon AC. Here AC is called carrier amplitude. And since in practice this carrier amplitude is typically measured in volts, hence the unit of amplitude sensitivity K suffix A is volt inverse. After the basic discussion, we move to noise performance of standard AM receiver, also called as envelope detector. For this, we first need to find input signal to noise ratio or pre-detection SNR. So here we consider standard AM, and after opening bracket we get S function T equals to AC cos 2 pi FCT plus AC into Ka MT cos 2 pi FCT. Here the first term is called carrier and the second term include a message signal M function T and called as information bearing component. In pre-detection SNR, we have to determine average signal power. And here average power of the first term is AC square upon 2, and that of second term average power is AC square Ka square upon 2 into P. Here P is assumed as average power of message signal M function T. And after adding we get AC square upon 2 within bracket 1 plus Ka square into P. So we can say that the average power of full AM signal is given by estimation of S square T, and it is equals to AC square upon 2 1 plus Ka square into P. Also, the average noise power over transmission bandwidth can be determined using expectation of N square T, which is equals to N naught into B suffix T, where B suffix T is called transmission bandwidth and N naught is called average noise power per unit bandwidth. Now the input or pre-detection SNR is equal to estimation of S square T upon estimation of N square T, and it is equals to AC square within bracket 1 plus Ka square into P upon 2 N naught into B suffix T. After this we have to find output or post detection SNR. For this, we consider output of a bandpass filter, or we can say input of envelope detector denoted by X function T. Here X function T is equals to ST plus NT, and NT is called filtered or narrowband noise. So we put ST as a double sideband full carrier signal, and it is equals to AC within bracket 1 plus Ka MT cos 2 pi FCT, and NT as a narrowband noise in terms of in phase and quadrature component, which is Ni cos 2 pi FCT minus NQ sin 2 pi FCT. Now combining the first and second common term, we get x function t equals to within bracket AC plus AC into KAMT plus NI into cos 2 pi FCT minus NQ sin 2 pi FCT. Now using envelope detection as shown in figure, it consists of series diode and RC filter. The output of an envelope detection can be obtained by taking envelope of input signal xt, and which is same as finding magnitude. So y function t equals to under root of AC plus AC KAMT plus NI square plus NQ square. This y function t is considered as output of an ideal envelope detector. But since ideal envelope detector is insensitive to phase, that's why phase is not considered here. And for our convenience and understanding, we assume signal is much larger than noise. Then we can use an approximation, that is under root of a square plus b square is approximately equal to a when we consider a is far greater than b. So using this approximation and consider signal much larger than noise and called as higher signal to noise ratio condition. And under this condition, y function t is approximately equals to AC plus AC KAMT plus NI. Here the first term is DC component, second term is a signal component, and the third term is in phase noise component. And in order to find post detection signal to noise ratio, we require signal component and noise component. Here DC component can be removed by capacitor called as DC blocking capacitor. So the output of blocking capacitor becomes AC KAMT plus NI. Here first term is scaled version of message signal and the second term is in phase noise component. From here we can find average signal power of scaled message signal, and it is equals to AC square Ka square upon 2 into P, where P is called average power of message signal. And from the second term, average noise power within message bandwidth W is equals to N naught into W. Here N naught is called average noise power per unit bandwidth. Now taking the ratio of average signal power to average noise power, and we get AC square K square upon 2 into P upon N naught into W. And after simplify we get AC square K square P upon 2 N naught into W, and called as output or post detection SNR. This output SNR is valid only under the two conditions. First is high signal to noise ratio, which means we assume signal much larger than noise, that is high